So I will try to present the reactor thermal hydraulics. Of course, it's a little bit short to do this. And so in the first part, I will talk a little bit what does this mean for other type of reactors. So you can see the parallel with the MSFR. And then I will present a typical model that high compressible flow that you may use in many applications for a molten salt. And at the end, I will show you some of the things that we are doing right now. So first question is why we need to do thermohydraulic design. This looks very obvious, okay? So this is a list of reference that you can check, okay? So let's go to the first part. So why you need to do thermohydraulic design? Well, the reason is very simple. It's because you need to check that the reactor verify some design and safety criteria. These look very obvious, but when you get into details, it's not so simple. And then, of course, the other reason is that you need to produce electricity, and this should be competitive. And this is a problem right now. So if you look the overall design process that you will see in other type of reactors, and probably we will use a very similar process. You usually start for a classification of the plant conditions. So what is normal operation? What is accidental conditions? You will say what are your requirements. So you don't want something to happen, for instance, during normal operation. You will need to check the phenomena, what is happening in those plant conditions, and then you will have to say which are the criteria. The criteria are the conditions that you will study with, for instance, the thermohydraulic design, and you will verify that they are satisfied by the design, and then you know that you are meeting your requirements. So that's the overall idea. It is very simple, but when you go to all the components of a reactor, it can become very complicated. So if we look at the example of the PWR, which is it is very well known, we have been working on this for decades now. There are, in general, we consider there are 4 conditions. So let's look at the condition 1, so normal operation. Then when you go to the requirements, you ask, of course, that at normal condition, there should not be a failure in any of the barriers of the reactor. So there are 3 barriers: the cladding, the primary circuit, and the containment. Now, okay, let's move forward. If we look at the phenomena, I'm not going to go through all the phenomena that you can have, but let's look at 2 very important phenomena for the fuel. One is the DNB, departure from nucleative boiling. This is happening when the heat flux go too high, and then you have this thin layer that will appear over the surface of the cladding. That will lead to the failure of the cladding, so the first barrier. Second phenomenon that is it is very well known is the fuel melting. This happens when you go too high on the linear heat flux on the fuel rod. So once you know what are the phenomena that may be a problem with the design requirements, then you need to look at the criteria. And here is not so difficult actually. The first criteria will be, okay, you should not be in DNB conditions. So you probably put some statistic conditions there, because you can never be 100% sure that things won't happen. And for the fuel melting, it's very easy, because you are just going to put a limit on the maximum linear heat flux on the fuel rod. And then because the conductivity of the pellet, you know more or less, then you can immediately know what is the center line temperature, which is the maximum temperature. So you put the criteria, and then you will run some safety studies. You will look at different scenarios, and you will use some thermohydraulic codes and verify that these 2 criteria are met. Now, what is the difference with the MSFR? The MSFR is a novel design, and Elsa explained this morning the main principles, so I'm not going through it. But as you already know, you have a liquid fuel, so here things are a little bit more tricky. There are some advantages, but there are some difference. So you already saw this morning, so we have a liquid fuel that is a coolant, but also it is a fuel. I will talk a little bit later, but that makes some significant difference in thermohydraulics. We don't have a control rod. In principle, we don't need it. That's a very good point, because control rods are a path for accident in other type of reactors. And we have the possibility of changing the geometry of the fuel during the accident or during normal condition, which is giving you like more degree of freedom in the design. All right, so let's look now what are the phenomena that are very different from other type of reactor, because that's going to impact the process that I mentioned before. So as Sandra mentioned this morning, you have the delayed neutron precursors that are now are circulating. This is really new, and although in principle it's not going to be a big issue, it's something that you need to take into account in the studies. Now, another important difference when you don't have a solid fuel is that you have a large core cavity. So in the cavity, you will be a very high Reynolds number, so very high, relatively high velocity. Inertial forces in the flow will be important. And then you will have turbulence. Now, turbulence is very nice. We use a lot in industrial application, but the problem is not so easy to model it. Now, and since the precursors are moving with the fluid, then that means that if you make a mistake with the flow field, then you do it also in the concentration of the precursors, and the beta effective, and so on. Now, the flow distribution, as I say, will impact the feedback coefficients, and will also change the temperatures on the core wall. And again, that's another issue. Here, we can think that the cladding of the reactor is actually all the structures that are around the core. Heat transfer is quite complicated in molten salts because you have conduction, like in the pellet, but you also have convection, and you have radiative heat transfer. So the salt can be, in some cases, considered as a semi-transparent medium. So you can transfer heat by radiation heat transfer. Another point that makes difference is you have phase change. So you may have solidification in some part of the reactor. And of course, you have the nuclear heat source, or the decay from the fission products. This means that you have volumetric heat source in your coolant, basically. So these are the things that you need to now consider, and that will be different when you do the thermohydraulic design. Let's just finish this comparison, quick comparison with other type of reactor. And here you have a table with some of the parameters, not all of them, for PWR, for a sodium cooled reactor, and then for the molten salts. Of course, this part is not finished because we are still working on the design, on the safety study. This is just given here as an example. As I say, in PWR, you have DMB, you have the linear rod power, clad oxidation, for instance. In the case of the molten salt reactor, we will looking at the maximum, for instance, the maximum salt temperature, because we know that we cannot go beyond some values. It will depend a lot if you're in normal conditions or if you are in accidental conditions. We will look in also the gradient of temperature on the wall, for instance, because that may create some problems related to thermal fatigue or so on. We look also the minimum temperature. You don't want to have solidification, at least not during normal conditions. And you may look to the maximum coolant velocity because of corrosion or other issues. Now, in the last row, I put the codes that people usually will employ for doing the thermohydraulic design. In PWR and also in SFR, because this is the flow is quite simple, not so, but actually it is fairly simple inside the core, because you have a principal direction that is the vertical direction. These are like fuel, the coolant channels. So you can use codes that are more or less simple, that are based on sub-channels approach. This is kind of Bernoulli modified equation with some correction because of the pressure loss. Or you can use porous medium approach. There you will consider that the reactor is like a porous medium. You will have a permeability, and you will calculate the flow. This is okay when you have a main direction inside the core. In the case of the MSFR, as I said before, this is a strongly 3D flow, so you will probably need to use a CFD code if you want to have a reliable prediction. All right. So what are the particularities of a molten salt reactor for thermohydraulic modeling? Well, you will have to solve the Navier-Stokes equation. This is not an easy task from numerical point of view. You will have to run coupled neutronics and thermohydraulic simulation. It's very, I mean, it won't be a good approximation if you try to do separate calculation like you do in PWR. You will have to run steady and transient calculations. That's very important. And the last point is what we are actually doing in some of our projects is you will need to look at the CFD models and be sure that they are well adapted to the specific cell phenomena that you may have in this reactor. So we'll go a little bit quick on this, but I want to give you an idea of what are typically flow governing equations. You will see that they are not so simple, and they are very non-linear, and that's the reason because CFD is not so simple. So we will look how do you get, very quickly, how do you get typically conservation equation for a fluid. And we will be considering that this flow can be approximated as incompressible flow. I explain in a minute what is that. So the first thing that you would do if you want to write the equation for a fluid is to get the conservation of mass. This is quite simple. Basically, you will follow the particles, the fluid particles, and you will use a control volume, and you will do the balance of mass on that. Then you will turn the volume to 0, and then you get the differential equation that you see here. Of course, getting this equation, I'm doing some approximation, like I'm considering that there are nuclear reactions are not changing the mass, that is, which is a very good approximation. But in particular, I'm considering that there is no change of phase in the solid. This is not true in some cases. So this equation will work fine if there is no solidification, for instance, in the solid. If there is solidification, then we'll need to change it. So you can see that for the mass conservation, you have a first derivative that is a local derivative over time, and then you have a convective term. This is basically the mass that is going in and out of your control volume. Now, a very interesting case, and that we use very often in many fluids, is the incompressible flow. Incompressible flow means that if I calculate the material derivative is the variation of something moving with the fluid. If this material derivative of density is 0, so basically density is not changing, then the conservation of mass will become a very simple equation that says that the divergence of the velocity should be 0. So this is very nice because it simplifies a lot the resolution of the equations. This approximation in compressible flow, it doesn't work in all cases. In a molten salt, will work if you don't have a too large variation of temperature. So the next equation that we would like to do is the conservation of momentum. There you will work with the second Newton law. You will do again the balance of forces. You will have this is the term, the acceleration term. Again, this is a material derivative. It's not a classical derivative. It has a temporal term, local acceleration, and then it has a second term that is very non-linear, that is the convective acceleration. And then on the right of the equation, you have the gravity force. This is a volumetric force, and then you have a surface force that comes from the stress tensor. Now, this equation looks fine, but actually we cannot solve it because we don't know how to get the stress tensor. Okay, so how we do that? Well, first of all, let's look at the stress tensor. This is a tensor, so it has 9 components. It is fairly easy to show that actually it's a symmetric tensor. So this is because of the conservation of the angular momentum. So you can show that actually there are only 6 components here that are independent. The diagonal are those that are normal to the surface, and the extra out of diagonal elements are those that are giving you basically the shear stresses, okay? So how we can solve this? Well, people use, they consider different type of fluids. One of the simple fluids that you can consider is a Newtonian fluid. In a Newtonian fluid, we will establish a relationship between the stress tensor and the rate of the formation of the fluid, okay? The idea is that you will write the stress tensor as a component that is coming from the thermodynamic pressure, so something that we know how to calculate in theory, and then another tensor that is all what is outside the pressure part. So the idea is that in a Newtonian fluid, we will say that there is a linear relationship between the stress tensor and another tensor that is the strain rate tensor. So what is this? This is a tensor that is telling you how the fluid is deforming because of the flow field. So if you have a rigid body, this tensor will be 0 because the relative distance between 2 points in a rigid body is not changing. Eventually, the body may displace, but it's not going to change. In a fluid, things are a little bit different. There will be a deformation. If you trace a line, the line will, or let's say a square, the square will change of shape as the fluid is moving. So this strain rate tensor is capturing that information. So the idea of Newtonian fluid is that you will say that there is a linear relationship between that stress rate tensor and the stress tensor. Now, the coefficients are the viscosity coefficients that probably you already heard about that. So these coefficients are thermodynamic property of the fluid. If we insert that constitutive relationship between the stress tensor and the strain rate tensor, we put that in the Cauchy equation, so the equation for the momentum, the conservation of momentum, then we finally get the famous Navier-Stokes equation, okay? Now, this equation actually may look a little bit difficult, this side here. Actually, this is not the difficult part. The difficult part is still on the left side because, again, this is a material derivative. So it has two components. It has a local acceleration, and then you have a convective acceleration that is a very non-linear term that we'll see it will cause many difficulties. So very often people use another approximation that is the Stokes hypothesis that will cancel this bulk viscosity that appears here. But if you consider that the fluid is incompressible, so what I said before, so the density is not changing, this equation will become very simple. We come in this way, and if you can you drop the index notation, then you can write in that other way. So that's for the momentum. What about the energy? Well, energy, the same idea. You take a control volume. You will be looking at heat transfer by conduction. Okay, we are working at microscopic level. You will consider also the mechanical work. You will have an irreversible conversion of part of the mechanical energy of the fluid. You will look at the pressure also effect on the energy. And if you consider all those things, you will be able to write now this energy conservation equation where here E is the internal energy of the fluid, okay? So again, so this term here is come from the pressure effect. This term here is the viscous dissipation, and this term here is basically the conduction. Now, we can do further approximations, and again, this approximation, here I'm presenting the Boussinesq approximation. This is something that we use in the models, in many of the models that we are using for molten salts. The Boussinesq approximation, basically what it's saying is that if we can neglect the pressure compressibility effect, so basically if there is a pressure variation in the fluid, we are considering that the density does not change. And if we have temperature variations that are not so important, this is a little bit tricky because the inlet and outlet, the reactor, you may have 100 degrees of difference and the density will change, but let's say that this is okay. Then if those two conditions are met, then we can consider that the variation of density will be only important in the gravitatory term. So what I'm saying there is that because of the density variation, then the gravity force will be changing in the part of the fluid that are higher temperature, density will be lower. Then the gravity force will be a little bit less. In those colder regions, actually density will be higher, and then the gravity force will be a little bit stronger. So we can approximate the gravity force effect by something that we call a buoyance force, and this or flotation force, and this force basically will be proportional to a variation of density that will depend on the salt expansion coefficient, and then the local variation of temperature. So if we use the Boussinesq approximation, then the Navier-Stokes equation will become much simpler. Okay, we will also assume that, like for instance, the viscosity is constant. The only thing that we consider may change because of temperature is this buoyancy force that comes from the density variation of the fluid. We can do the same thing for the energy equation, and then you will get a very nice and simple equation, what you can see here, that may look like you have done a lot of approximation, but actually works quite well in many of the cases that you may be studying. All right, so up to here it looks not so, let's say, not so complicated. These equations look fairly simple. But as I said before, this material derivative, it is very nonlinear. And actually, this equation has only a few analytical solutions. If you want to solve it numerically, you will see that the nonlinear term may cause some instabilities that actually everyone knows, and we call this the turbulence. So the Navier-Stokes equation, depending on the velocity of the flow, may lead to a laminar flow type or a turbulent flow type. Why is that? Well, because in this equation, you can think that this is the pressure, this is the force coming from the pressure gradient. This is the buoyancy force, so the force coming from the difference of density in the fluid, like a natural convection, everyone knows probably. This will be the term associated. And this term here, this is the viscous forces, okay? And what we have in the left, these are the inertial forces. These two, the inertial and the viscous forces, are the two that will decide, the difference between the two will decide whether the flow it is laminar or turbulent. If the velocity of the fluid are high enough, the inertia term will become very important, the equation will be very nonlinear, and then you will have turbulent. On the contrary, if the viscous forces are very important, like close to a wall, then the solution of the equation will be a little bit more easy. You have less instabilities, and you will have a laminar flow situation. So, as I said before, the Navier-Stokes equation is highly nonlinear, depending on the Reynolds number. Reynolds number is telling you what's the ratio between the inertia and the viscous forces. Depending on the Reynolds number, you may be in the case of turbulent flow, what you can see here, or laminar flow. Laminar flow is a flow that you can think like layers of fluid that are sliding one over each other. You may have no luck and be in the middle of so transitional flow. So sometimes it is laminar, sometimes it is turbulent. So, turbulent flow may look like a random flow, but actually it is not, because you are conserving the energy, you are conserving the momentum, so and the energy. So it's not a purely random flow. So how we can solve this? Well, you could think that you can try just to solve the Navier-Stokes equation at a very, very refined mesh, but that is very difficult. So people at the very like 34 years ago, they implement a method that led to solving this equation in an easy way. Before going to that, let me just very briefly explain what is turbulence. Turbulence is not so simple to define. You can say that it's a dissipative flow that has nonlinear fluctuations and has three-dimensional vorticity. Vorticity is a very specific term. It means a rotation of the fluid around some point. If you want to characterize turbulence, you will probably mention all these 5 features, okay? Like you have fluctuation of the properties that is very nonlinear. So the flow was laminar, and then when you increase a little bit the velocity, then it becomes turbulent. This was happening at a threshold velocity. Vorticity, actually, as I'm saying, this is vorticity is something that will tell you about the rotation of the fluid about some point. Vorticity, it is very important in turbulent flow, and you will have eddies, so like structures that are rotating that will develop in the flow. We don't see very well here, but it is this is shown in this graph. You will have dissipation. So basically, the energy from the large eddies, the large vortex, will be transferred to the smallest one. And the dissipation of that energy actually will happen at very, very small vortices that are the one that, because of the size and the velocity that they have, they will basically dissipate the kinetic energy and transform in thermal energy that you actually is very, very small. And another point is diffusivity. So when you have turbulence, you will have a higher transfer of heat, higher transfer of momentum. So this is the reason because many industrial systems use turbulent flow, because the heat exchanger will be much more efficient in this regime. So how do you model turbulence? So we still have the Navier-Stokes equation, but how do we numerically solve it? One way of doing this is to use basically a theory of stochastic process. So you will try to decompose the different variables of the flow in a mean value, average value over time, and then a fluctuation. Now, it is important to understand the difference between non-stationary flow and stationary flow. A stationary flow, you have turbulence. This is, for instance, the velocity. As in some point, you can see that you have some fluctuations, but you can see that the mean value more or less constant. this case is very easy to, I mean, it's not so difficult to calculate the average value, for instance, of the velocity, because you will calculate the average over some time. Now, this is a different situation. It could be, for instance, an accident in the reactor where you have a loss of flow, and the flow is decreasing, but you still have turbulence. So if you want to calculate the average value there, it's a little bit more difficult. Still, it can be done. So the idea here to solve the Navier-Stokes equation will be then to look at the mean value, the average value of different parameters. And then you will be using some rules that are named the Reynolds average rules. These are rules very simple to understand. You can demonstrate then that if you calculate the average of the sum of two functions like temperature and, I don't know, velocity, then it is the summation of the average and so on. So this is very, very simple to understand. Now, so the idea that this was the idea of Reynolds was, he thought, okay, let's decompose each of the parameters, the pressure, velocity, the density, the temperature, in the mean value, and then the fluctuation, and then inject that in the Navier-Stokes equation and see what we get. We did that because we don't want to do what is named DNS method, so direct numerical simulation. That means that you want to solve the equation at very, very low level. So if you do that, you will see that, so you inject those things, you use the properties, you will see that now you will get a new set of equations, okay, for the mass, momentum, and the energy. And for the mass, it looks exactly the same as before, except that this is the average velocity. For the momentum, it looks quite the same, actually. And the energy, more or less the same, okay? So this is the material derivative that I was mentioning before. You have a local derivative, and then you have a convective term that is very non-linear. Same here, okay? This is the non-linear term that is actually causing the turbulence. Now, if you look at, for a second, in the momentum equation, you will see that it looks quite the same as before. We have the average value for each of the quantities except this new term here. So what is this new term? This is the Reynolds stress tensor. This is a turbulent viscosity that is caused because of these fluctuations. Of course, we don't know how to solve this because here we have an average of the fluctuations, and this is not straightforward how to get this parameter. In the energy conservation, we have the same problem. We have here the average of the fluctuation in velocity and fluctuation of in the temperature. So we don't have a model for that. So the idea was, yes, maybe this is, I'm going very quickly, this is an explanation why this term is not zero. You may think, okay, if I multiply two fluctuations and calculate the average, that will be zero. Well, unfortunately, in a flow, it's not the case. This is showing the velocity profile, for instance, near a wall. And you can see this fluid particle is, because of fluctuation, is jumping a little bit up. So to a region where the velocity, the mean velocity is a little bit higher. So here, the fluctuation of velocity in the vertical direction is positive, but in the horizontal it's negative because it goes to a region where the rest of the fluid is going a little bit faster. So if you calculate the average there, this is not zero, it is negative. This is just to show you that this term is not zero in general, especially when you're moving away the walls. So the other point that is important is that this Reynolds stress tensor, so this term here, actually can become much larger than the viscous stress that we know how to calculate when you go to the bulk of the fluid, not near the wall. So how we solve this? Well, people when they develop this RAM method, so RAM means Reynolds average Navier-Stokes equation, they decide to link the stress tensor to some average values in the fluid. And here, for instance, this is the strain rate tensor, but calculate with the average velocity. So we know how to do this. This is come from the equation. So the idea was that you will link the stress tensor to the rate of the formation of the fluid, but in average value. And then we came with a new parameter. This is the turbulent kinetic energy. So this is the energy that is associated with the fluctuation of the fluid. And of course, we don't have a model for that in principle. But then you will need to add more closure equations, and you will need to add a closure equation to say how this turbulent kinetic energy is being expanded in the fluid. And so these are what is named the two model equations. So basically, you will say these are semi-empirical equations, of course, that will say, okay, how the turbulent kinetic energy that appear in here will be dissipated. So that leads to another variable that is the turbulent energy dissipation. So this will lead to different closure models that probably you may have heard about, like K-epsilon model or K-omega model and so on. These are all semi-empirical models that will try to provide physical meaning for these parameters and then let you calculate the stress tensor using some relatively simple equations that are related to the average value of the fluid properties and not to the fluctuations. So if we use these things, then now you get the Ram's equations, so the Reynolds average Navier-Stokes equations. These equations are providing information about the average value of the properties of the fluid, like velocity, temperature, pressure, and so on. And these equations are a little bit simpler to solve, and they do not require a mesh that is at, I would say, micrometers of length. Of course, there are some issues, like you need to know what is the turbulent viscosity, you will need to know what is the turbulent diffusivity, and you will need to use closure equations for those particular things. So here, for instance, if we look at the Navier-Stokes equation, we have, this is the local acceleration I was mentioning before, this is the convective acceleration. Here is a pressure term. You can see that the turbulent kinetic energy is adding like a pressure, a contribution to the pressure in the fluid. Then we have the viscous force, and the viscous force has the viscous and the turbulent viscosity effect. And then this is the buoyance force that is coming from difference of temperature in the fluid. So these are typical equations that we may be solving in the case of the molten salt reactor. So if you want to calculate, to numerically calculate the equation before, what you will do at the beginning is to use a guess for the velocity and pressure. Then you will calculate the K-epsilon equation that I didn't show because they're a little bit complicated. Once you get these two parameters, you recalculate everything, and then you finally converge at some point. All right, one last thing, and to finish this Navier-Stokes part, if you move too close to the wall, unfortunately, you have a large gradient of, for instance, of the temperature or the fluid velocity, and you will need to use a mesh that is very, very refined there, and then you will lose all the advantage that we had before by using this RAM method. So what people do there is they will use a semi-empirical profile for the temperature and velocity that is named law of the wall. This is a way that basically you avoid to numerically solving what's going on there. You have some analytical or semi-analytical solution. You put it there, and then you start your mesh a little bit away from the wall. Now, the only thing here is that you have to be sure that the wall of the law that you are using, it is okay with a salt, because some of them, for instance, have been obtained for fluid like water. All right, so that's a typical example of what you can see, how it can be a typical thermohydraulic model. This is a simplest model. You can have a more complicated model, like if you want to study compressibility effects that may happen in some type of accident, then the equation will be a little bit different. So let me just go very quickly on what is CFD, but we already seen it. CFD is these are just numerical methods that let you obtain approximate solutions for the fluid dynamics and the heat transfer. This is something that was not possible 30, 40 years ago because we didn't have the computation capability to do. And so it started, I would say, at the end of the 80s. There are many different codes. There are some commercial codes like Fluent, StarCD, CFX. And then you have some other codes like OpenFOAM that we use. I think many people here are using it because this is an open source code, and it works fairly well. So I mentioned before, to solve the Navier-Stokes equation, the easy way to do it is to use a Ram's method. So you calculate the average parameter. But this is the only, I would say, the simplest way to do it is the one that is more often used in the industry. But there are other methods that are more precise. And you can think that there are actually 4 families of approach to solve the Navier-Stokes equation. The one that we have seen is the Ram's, so here on the top. Here on the right, you can see a fluid structure. This could be an eddy or a vortex of different size. These are the small one that will dissipate the energy, as I said before. This is the bigger one that may be occupying whole pipe. So the idea between these four or three different families is that the run method, it is basically even nearly not considering the structure of the big eddies. Maybe if very large, you can see it. Then you have another family of methods, the LES, large eddy simulation, that they will put a filter in the filter in the resolution of the Navier-Stokes equation. They will consider some vortex up to some size, and then the rest of them they will just model by a closure equation. And then you have I would say the more exact method, that is the direct numerical simulation, DNS method, that basically make no assumptions in theory, and will basically resolve all vortex of all sizes. Okay, this method, the problem is that it's only practical when you have a very simple geometry like a pipe with two planes or a circular pipe, and then you may want to use LES method. This may be okay if you want to work in some component of the reactor, but it's nearly impossible to use this at the scale of the full reactor. And then you can have an hybrid method that will mix LES and then runs method. This may be possible, maybe someday at the scale of the MSFR. Right now, we are mostly working runs method at the scale of the reactor because we still need to couple this to the neutronic part. Let me just, I will just move forward this. In nuclear industry, the use of CFD started about 20 years ago for the calculation of PWR fuel assemblies. This is a list of some of the applications that you have currently in the industry. So there is more and more interest because this lets you access to many more details on the fluid conditions. This is an example of simulation that you can see in MSFR. You have seen also this morning in the presentation of Elsa. You have a lot of information. You can look at what's the temperature over the world. This will be impossible with other type of method. So one important thing when you want to develop a CFD model is that you need to think about the phenomena that you want to capture in your CFD model. So you need to first identify what's the problem that you want to study. Then people use very often something that is called PERT. It's a phenomena identification ranking table. This looks very obvious, but it's basically making a table what you know and what you don't know about your fluid. And it's very important if you want to develop a CFD model that works in a fluid. So I will show an example of that. This is a list of recommendations that you have when you develop a CFD model. I'm not going through it because we don't have time, but the information is in the slides. And this is taken from a report from the OECD. And this is like kind of best practice for people using CFD in nuclear reactors. So you can, they are fairly easy to understand. So I will just move forward this. This is about the mesh, the shape of the cells and so on. And let me move to the last part of my presentation. This more focus on what we are doing in SAMOFAR. So I talk in the first part very quickly about the modeling effort, and then we talk about some experiments. So as Sandra mentioned this morning, the only way you can model the MSFR with some precision is that you do a coupling between the neutronics and thermohydraulics. This is probably the easy way of doing the coupling. Neutronic will tell you what's the power distribution in the reactor. Thermohydraulic, we calculate the temperature profile and also the variation of concentration of precursors, and then it will tell the neutronic code what is the temperature profile and what is the concentration of precursors that we'll use in the next iteration. So feedback effects, as we said this morning, are very important. You have Doppler effect, but you have also the effect coming from the density of the salt. And then delay neutron. This is important because the fraction of delay neutron that has an impact on the kinetics of the reactor. Now about turbulence, as I said before, you can use a RANS model. This is widely used in the industry. Now the bad news is that usually it's not so accurate. I mean, when you don't have experimental data, you can do a RAN model and maybe you are 20% off. So that may be not a big deal, but if you want to run experiment and design experiment, you need to improve the accuracy. So one thing we have been doing in the modeling part, in the project was actually develop an utility that it is able to fit, basically based on experimental data, your RAM model, so you know that it is not off more than 5%, let's say. Another point that I mentioned at the very beginning is solidification. So this is a very important key phenomenon, and up to now there is not that much simulation effort on this, especially in ternary alloy, like what you have in the salt that you use in the reactor. So why is this important? Because you need to, for instance, if you have solidification on some part in the reactor, that will change the heat exchange, that will change the velocity of the fuel. And also because if you have some solid phase that appears somewhere, you need to know what are the thermodynamic properties, like the conductivity, and the only way you do that is if you can model the solidification. Now, the solidification, modeling the solidification is not very easy, especially if you go to the microscopic level, because you will need to take into account many things, like the velocity of the solidification interface, the undercooling temperature, and the fraction of dissolved gases, and so on. So we have developed two models, one macroscopic model that is an enthalpy model, and then a microscopic model that basically is following the growth of the different phases, solid phases in the salt. Regarding heat transfer, in the salt, things are a little bit more complicated than in water because you have radioactive heat transfer. And the salt can be considered as a semi-transparent medium. So that means that if, let's say here you have three particles, okay? The particle may be exchanging radioactive heat outside a band. A band is a region where the fluid will absorb all the energy. And inside the band, so where the fluid is absorbing all the heat radiation, basically what will happen is that the thermal conductivity of the fluid will be increased by this, the presence of this band. So we have been doing also simulation, like this is a porous medium made by cylinders, and trying to study how radioactive heat transfer will change things in the salt. So now let's look very quickly on the experimental part. There are two main experiments in the project. One is SWAT, the other one is Dynasty. SWAT is done in Grenoble, Dynasty is done here. In SWAT, what we are looking is at heat transfer in very simple geometries. We are studying solidification, so we want to validate the numerical model I mentioned before. We look also flow in open channel. You may have a free surface somewhere, and that's not so simple to evaluate. We may be able to look also radioactive heat transfer effects. So the idea in SWAT is that we have two tanks that have a difference of pressure, and we will make circulate the molten salt through a globe box where we put some element that we will be testing. This is another example of experiment that is running right now. It's a solidification experiment. Here we have a furnace, electric furnace, that will keep the temperature in this graphite crucible. Inside here we have a molten salt, and then we have this cooler that is an annular cooler where you have an argon flow that go down and then it go up. Okay, so that will decrease the temperature and will induce a solidification of the salt over the surface. So the idea here is to study how solidification progress in, let's say, without any convection or very little natural convection. And then the nice thing is that this cooler can rotate about itself, and then we can study solidification in under a convective velocity field. And then, as I mentioned, we have also another set of experiments that is run here in Polimi, the Dynasty loop. The idea is to look at the how it works natural convection in this type of fluids, and what are the stability maps, and so on. This is important for, let's say, for instance, if we want to design a passive removal system, or even maybe in some region of the reactor, like I forgot the name, in the draining tank of the salt. All right, yes, moving in the opposite direction. So to finish, what are the perspectives? The idea is that this year, from the summer and on, we will be running the experiment in SWAT and Dynasty, and we will start hopefully validating the numerical model. We probably will find some surprise, and we will need to correct the model. So, but that's very exciting, I would say. We are expecting also to have some thermodynamic data coming from WP2. This may change the properties that we are using in the simulations, and then who knows, maybe we'll see some things. Once we will have a best estimate models, I would say, we will integrate them in the multi-physics codes that Danny will mention later, and we'll run some of the calculations and see how things change. And the idea will be eventually that at some point we can verify the design and safety requirements that I mentioned at the very beginning. Thank you very much.